Types of aqueous solutions. Two familiar solutions: salt water, sugar water. Salt water is a homogeneous mixture of sodium chloride in water, and sugar water is a homogeneous mixture of sugar, sucrose, in water. And if you imagine doing this in your kitchen at home, pour a teaspoon of sugar into a cup of water and you stir it, the sugar seems to disappear, right? And the same thing with the salt. You put the salt in the water and you stir it, and it's like, it's magic, it disappeared. We're just used to it, so we don't think it's cool anymore. Did the sugar and salt disappear? No, they're still there. You know, because if you taste the water, it's not going to taste like plain water. One of them will taste nice and sweet, and the others could be nasty salty. How does that happen, though? How does a solid go into the liquid and become part of the liquid? We're going to talk about that. Probably more than you want to talk about it. So what happens? Well, there is a competition between attractive forces when we try to mix a solid and a liquid together. And in a later chapter, we're going to talk about what exactly these interactions are. But for now, we're just going to talk about them as attractive forces. So there are attractive forces between the solute particles. So the sugar molecules. Why are they a solid at room temperature? Because they're attracted to each other. Otherwise, they'd fly apart and be a gas. So there's attraction between the sugar molecules. There is attraction between the liquid molecules, the water molecules in the solvent. That's why the water is a liquid sitting in the cup and it doesn't fly off as a gas. So there are attractions there. And those are the solvent-solvent attractions. And then we also have some attractions between the solvent molecules and the solute particles. And so in order for the sugar to dissolve in the water, it has to be able to mix in with the particles of the solvent, of the water. So it has to break attractive forces between the water molecules. We have to break attractive forces between the sugar molecules and replace them with attractive forces between the water and the sugar molecules. Not all things dissolve in water, and it depends on the relative strengths of these three different kinds of interactions. Yeah, metals won't dissolve in water. Well, most metals. Alkali metals will. They'll react and pop and fizz and all kinds of stuff. But like iron won't just dissolve in water.
So what about like
Pop
pop rocks?
rocks. It's an excellent question. I remember feeding those to the neighbor's collie. He didn't like it. He was fine. Wouldn't let us. He wouldn't eat anything we gave him after that. Smart dog. Very weird childhood memory. And then pop rocks went away for a while because they were so dangerous. And then they brought them back again. I don't know if they're different or not, but yeah, pop rocks. What about pop rocks? I'm going to have to Google that because now I'm really curious. There is obviously some sort of a chemical reaction going on there that's probably giving off like carbon dioxide in a sort of explosive way. Not really probably a combustion reaction, but it is a process of dissolving, but it's an unusual one. Yeah. But yeah, if you have questions, even if they seem completely off topic, go ahead and ask me, and I'll Google it during lab, because somebody asked me a great question yesterday and we talked about it, so that was cool. Okay, so a water molecule. This is one of those places where in order to talk about this, we have to talk about these intermolecular attractions and some things that we don't get to until later. But if we don't talk about this solution stuff now, then we can't get to that later. And so we kind of just have to jump in somewhere and hope that we can swim. So on a water molecule, there's an uneven distribution of electrons. Now, we talked about oxygen and hydrogen are both nonmetals, And so when they form the compound water, they do that by sharing electrons, right? They don't make ions like sodium and chloride do. They share the electrons. Well, the thing is, when you share something, you don't necessarily have to share it equally. You ever shared a bed with someone and you wake up in the middle of the night cold because you've only got one leg under the blanket, right? Are you sharing the blanket? Well, technically, yes, you're sharing the blanket, but the other person has more of it, right? So that's what happens when oxygen and hydrogen share electrons. Oxygen hogs the electrons. He's stronger, pulls the electrons away. So while oxygen is not an anion and hydrogen is not a cation, there is a partial charge here. So this end of the water molecule is a little bit negative because oxygen's pulling the electrons towards it. And the hydrogens are slightly positive because they're getting their blankets taken away. Not completely, but partially. And so this funny thing that looks kind of like a D with bad posture, lowercase d, this is a lowercase Greek delta, and we use that to symbolize a partial charge. So this is not a -1 charge. This is much less than a -1 charge. Maybe it's an eighth or something. Yeah. Exactly what it is doesn't really matter at this point. But it's a little bit negative, and this end is a little bit positive. Well, what happens when you have positives and negatives? They're attracted to each other. When we put sodium chloride into the water, it separates into sodium ions and chloride ions, and those were ions in the solid as well. They're not forming the ions, they're just there. The sodium ion is attracted to the negative end of the water molecule. The chloride ions attracted to the positive end of the water molecule. Water is a little bit like, a two-faced friend, right? Yeah, right? So the water is going to be whatever you want it to be. This is not going to be the honest person that's going to tell you how it is. They're just going to suck up to you and just, try to be happy with you. And so with sodium, water turns its negative side toward the sodium and attracts it. With the chloride isn't like that. It turns its other side to the chloride. And so both the cation and the anion have attractions to the water molecules. Okay? There are also attractions between the sodium and the chloride ions. Now this is a +1 charge and a -1 charge. This attraction is much larger than the attraction between a -1 and a maybe +1/8 or something. But what if you get a whole bunch of water molecules surrounding the chloride? Then all those little attractions add up, and they can add up to be greater than the attraction for the sodium. So each of these ions basically gets surrounded by water molecules, pointing the end that's attractive to that ion. And over here is the negative chloride ion being attracted and surrounded. So this is a very non-politically correct example. So you could think of this as, here we've got, this would be a little boy and a little girl, and, they're with this school group, and here are the bad guys, and they're luring them away with candy, right? I know, horrible. But you might remember it. I'm not advocating that is a good thing to do at all. But you can imagine, right? Some weird cartoon story or something. So this sodium ion gets lured away by the water molecules. The positive ends of the negative ends of the water molecule surround it and sort of replace what it had in the sodium chloride solid. And so now it's surrounded by these water molecules, and it's free to just move around in the water. And so that's what happens. The water molecules come in and they lure away all these different ions until they're all separated. The result of this is now we have a solution that has charged particles that can move. So this sodium ion can move around in the water. It's not self-propelled or anything, but just it can move. And this negative ion can move. Because we have charged particles that can move, this solution will conduct electricity. Pure water does not conduct electricity. Yes?
If there was an equal amount of water and sodium chloride, would they still make them away?
That's a good question. So let's just go back to that picture real quick. What if you had an equal amount, let's say an equal number of water molecules to ions? And let's say you had like 5 sodium ions and 5 chloride ions and 10 water molecules. Would they still be able to pull it away? No. No, they wouldn't. They'd pull away a couple, maybe, but the rest of them would stay. It does work similarly for sugar, yeah. And we'll talk about that in a minute. Usually when we talk about a solution, we're talking about a huge excess of water. Now, some things are very, very soluble in each other. We'll talk about that as well. Alcohol and water, they're both liquids, but you can put a little bit of alcohol in water and it will dissolve, or you can put a little bit of water in alcohol. That's what I said the first time. Or a little bit of, I'm going to start that one over. You can put a little water in some alcohol, or a little alcohol in some water, and it'll dissolve. That doesn't work with something like sodium chloride. If you put a little bit of water in a bunch of sodium chloride, it doesn't dissolve. But if you put a little bit of sodium chloride in a bunch of water, it dissolves. So it gets a little complicated. So if I put salt into water and I have a conductivity apparatus here, I've got a battery and a light bulb, and if I touch these two probes together, the battery would cause the light to go on. But these probes are not touching each other. They are in contact with the salt solution. The electric current can flow through the salt solution because of the sodium and chloride particles that can move and carry the charge. If I do the same thing in a sugar solution, and sugar and salt look a lot alike, don't they? Vanessa, they look a lot alike, right? We looked at those yesterday. If I put sugar in here, the light bulb won't light up. Because when sugar dissolves, it does not form charged particles that can move. And so it cannot conduct electricity. So an electrolyte is a substance that dissolves in water and forms a solution that conducts electricity. These are going to be soluble ionic compounds. Now, where do you hear the word electrolyte in everyday life? Gatorade, yep, or Powerade, right? It's like, oh, we've been exercising, we need to replenish our electrolytes. Well, what are they talking about? Those are soluble ionic compounds. When your body sweats, you lose sodium ions, potassium ions, etc. through your sweat. And if you've lost a lot of those, just drinking water is not going to be enough. You need to replace the electrolytes. Of course, the thing that they, kind of gloss over is that most people exercising do not sweat enough that they really need Gatorade, right? You just need water because you're mostly just losing water. But now the guys that have been playing football and practicing out in the middle of the afternoon when it's 106, those guys need Gatorade. They do. So those are electrolytes, soluble ionic compounds. They'll form solutions that conduct electricity. So what about the things that don't? Those are non-electrolytes. Non-electrolytes will be most molecular compounds, such as the sugar. Sugar doesn't conduct electricity dissolved in water. Salt does. Any questions? Yeah.
Just going back to like Gatorade, so the reason you would want to intake electrolytes is because you're sweating out them?
Mm-hmm. Yep.
So like your sweat has like electrolytes in it?
Yeah, your sweat has salts in it. Okay. So personally, I don't remember ever sweating this much, but I have so far, well, actually all 5 of my sons have played tackle football, and 2 of them are still doing it. And, they go to practice, and they come back.
Yeah, you heard that too? So 5 sons.
I have 5 sons.
Wow.
That explains a lot, doesn't it? 1 daughter. She's more work. 6. She's more work than all the boys. This is a vacation for me. You guys are so fun. Anyway, so if Michael comes home from football practice, I mean, he's drenched, right? His clothes are wet through. Hopefully, yeah, they don't smell good either. Hopefully, he'll put them in the laundry. But if they were to dry out before they get washed, you can see crusty white stuff on there. What is that? Salt. It's the electrolytes, right? So that's what you've sweat out. Now, you have to sweat a lot to lose a significant amount of electrolytes. But then, if that's the case, then Gatorade will help replenish that. Yes, if you're vomiting or having diarrhea, you're going to lose electrolytes big time. Sweating, it has to be extreme, but contact football, that's pretty extreme. And my son and his friends have started doing this. What's actually better than Gatorade is Pedialyte.
Yep.
Because Pedialyte has all the electrolytes in it and just enough sugar that you can get it down, right? Gatorade has way too much sugar. So it's coconut water, yeah. Yeah, so some bottled waters say, it includes electrolytes. And yes, it is the same thing. Now, tap water has electrolytes in it. Does it have a lot? Well, it depends on whether it's hard water or soft water. But it does have some dissolved minerals, some dissolved salts in it. Like deionized water or distilled water does not. So, personally, I think all water kind of tastes the same. But I know some people have very definite opinions that this water tastes good and that water does not taste good. I recognize most water tasting like water, and then there's some waters that taste nasty, right? They get sulfur in them, or just like, ooh, how can you even drink that? But then the others are like all the same to me. But some people have very distinguishing palates, and they can tell the difference between different bottled waters. Well, why does the water taste different? It's those little tiny bits of electrolytes that are dissolved in there. Because pure water is pure water. It just doesn't really have much of a taste. So you're actually tasting the things that are dissolved.
I've noticed that spring water tastes different.
Mm-hmm. Well, spring water is groundwater, and so usually as the rain percolates through the ground and gets into that underground aquifer, it will pick up dissolved ionic compounds. It'll pick up minerals. And so depending on where you're getting your spring water from, it will have a different taste. Now, my mother-in-law lives out in the country outside of Reedley, and her well water does not taste very good. And it's super, super hard, and it just corrodes everything. But my family has some property at a lake in Minnesota, and it's very primitive. 1 step up from a tent, my dad says. We got a hand pump to get water out of the ground. No electricity. We got an outhouse down the path. It's a 2-holer, though. But that water tastes so good. And you're like, oh, it's just water. No, it's just really good water. It's got like just the right amount of stuff in it, right? And so could you reproduce that? Sure you could. Is it worth doing? I don't know.
I was going to say mountain water tastes really good.
Mountain water tends to taste really good too, yeah. So that's what makes water different. Well, that was fun. Sugar dissolving in water. So sugar is not an ionic compound, but sugar has a lot of hydrogens and oxygens on it. And those hydrogens and oxygens are not sharing equally. Again, the oxygen is being a hog with the electrons. So the oxygen end, the negative end of the water molecule, is attracted to these slightly positive hydrogen atoms on the outside of the sugar. Yeah?
I don't want to back if you don't mind. When there's an uneven distribution of electrons in the water molecule, is that saying that the electrons
So,
And those last two spots are very.
so when there's an unequal distribution of electrons, exactly what do I mean by that? Is that pretty much what you're asking? The electrons are matched up with the protons. So water has, oxygen has 8 protons, it's got 8 electrons. Each hydrogen atom has 1 proton and 1 electron. So there's 10 electrons in the water molecule. But instead of the oxygen and the hydrogen sharing them equally, the electrons spend a little more time around the oxygen than they do around the hydrogen. And so it's just where the electrons are in the molecule. It's a little hard to explain right now because I haven't told you all the other stuff. So because this sugar molecule has this uneven distribution, it will be attracted to the water molecules, and the water molecules can usher, take away the sugar molecules and cause them to separate. But the molecules remain intact. The sugar molecule doesn't come apart. It just separates from the other sugar molecules. So there's no charges, no ionic charges here, no ions, and so this will not conduct electricity. Electricity is a flow of electrons. And so in order for electrons to flow through the circuit and make the light bulb go on, there has to be something that can carry the electrons, and nothing here can carry electrons. We've mentioned acids, and we learned how to name them. We said that acids are molecular compounds that ionize when they dissolve in water. So an example is HCl. HCl, 2 nonmetals, it's a molecular compound, but when you put it in water, it separates into ions. The hydrogen is like, I need to get away from you, chlorine. Here, you can have my electron. And they separate. And so then we've got hydrogen ions and chloride ions, and those get surrounded by the water molecules just like the sodium and chloride ions did. So an acid like hydrochloric acid is, the molecules are pulled apart completely. It ionizes. It didn't have ions before, but it becomes ions. It's ionized. And so an acid like that is called a strong acid. A strong acid is not necessarily more dangerous than a weak acid. A strong acid is a strong electrolyte, means that the particles separate completely. We can also have a weak acid. 2 examples here are hydrofluoric acid and acetic acid. Here we have an illustration of acetic acid. When you put hydrogen acetate into water, it does form ions, but not all of the molecules form ions, just some of them do. So there are some ions in here, and this solution will conduct electricity a little bit, but if we see the light bulb, it will glow weakly instead of strongly. So a weak acid forms a weak electrolyte, doesn't form as many ions. And why is that? Well, apparently the hydrogen ion and the acetate ion get along better than hydrogen and chlorine do. So strong electrolytes dissolve completely as ions. There's no molecules left, just all ions. So strong electrolytes would be the soluble ionic compounds and the strong acids. And I'll tell you which ones those are in a minute. And then we have weak electrolytes. They dissolve mostly as molecules, but a little bit as ions. And so these are weak acids. Now something like sugar didn't make any ions. Sugar is not a weak electrolyte, it's a non-electrolyte. So we have strong, weak, and not at all. Sodium chloride is a soluble ionic compound. When it dissolves, all of the ions separate. We don't have any formula units staying together. They all separate, so this is a strong electrolyte. We've got a picture, yeah. So this is a non-electrolyte, sugar, dissolves in the water, but it doesn't form any ions, and so the light bulb will not go on. Here we have a weak electrolyte, acetic acid. It forms some ions, so it will conduct electricity a little bit, and so the light bulb's like kind of glowing, but just, just barely. That's weak. And here we have the strong electrolyte. They all separate into ions. Lots of things to carry the charge flows better, and so the light bulb gives off a strong light. Any questions? So which of these aqueous solutions, so they're all dissolved in water, conducts electricity? Well, what kind of things conduct electricity? Ionic compounds. So are any of these things ionic? A is, right? KBr, metal, non-metal, ionic compound. So this one, this one will conduct electricity. What about this guy? Well, it's not ionic. Carbon, hydrogen, and oxygen, all nonmetals. So you don't have the ability to name that, but you should be able to say, well, that's a molecular compound. Is it an acid? Probably not, because it doesn't start with H. And in here, if I want you to know that it's an acid, it will start with H. So not an acid. So that's not going to conduct electricity. What about this one down here? Again, the carbon, hydrogen, oxygen. It ends with hydrogen. Does that make it an acid? No. It has to start. This is an alcohol. Doesn't conduct electricity. Yes?
Will we be able to get to the point where we can compare like acids and ionic compounds and see which one would be a better conductor?
Yes, because there are 6 strong acids. And so strong acids are strong electrolytes. They're on par with the ionic compounds. And all of the other acids are weak acids. And so they're not going to conduct as well as ionic compounds.
So
It's just those 6.
We need to memorize the 6 strong ones.
Yep.
Is it a rule that ionic compounds always conduct electricity?
It's a rule that ionic compounds that do dissolve in water always conduct electricity. There are ionic compounds that do not dissolve in water. So when the ionic compound dissolves in water, we get separated ions, but not all of them. Not all ionic compounds dissolve. So in very simple terms, we can say something is soluble if it does dissolve, or insoluble if it does not dissolve. Now the truth is, as you will learn in Chem 1B, if you take that, even an insoluble compound dissolves to some extent, but it is not important. So something like silver chloride is considered to be insoluble. So maybe you have 50 gazillion silver and chloride ions, and the number that dissolve might be 100. So yes, some of them dissolved, but not enough to be worth even thinking about. So we tend to talk about all or none, but we recognize that there's just not black and white. So when an ionic compound dissolves in water, the cations and anions separate from each other, and that's called dissociation. They disassociate, right? They get away from each other. So here we've got sodium sulfide. This has 2 ions, sodium ions and sulfide ions, and so it separates into those 2 ions. We can predict the charge on sodium ion because of the periodic table. We know the charge on sodium ion, sulfur ion, sodium ion, whatever. This 2 came from looking at this formula and seeing there's 2 sodium ions in the formula. There's 2 sodium ions and 1 sulfur ion, and so when I split them apart, I've got 2 sodium ions and 1 sulfide. This is the formula for sodium ion. It's not Na2, 2+. It's an individual ion. There are polyatomic ions, and when these dissolve, the polyatomic group stays together. So here we've got sodium sulfate. So we learned to name these by identifying two ions, right? Sodium and sulfate. And when this dissociates, it separates into two ions, sodium ions and sulfate ions. And so this sulfate group stays together, it doesn't come apart. Silver nitrate dissolves in water and forms an electrolyte solution. Put silver nitrate in here. This has a polyatomic ion. The silver ions and the nitrate ions, they separate from each other. You put silver chloride in solution, and it just sits there. Doesn't dissolve. Teeny tiny bit dissolves, but it's not worth thinking about. So why do some ionic compounds dissolve and others don't? That's complicated. Depends on lots of different factors. So the best way to be able to identify what dissolves and what doesn't without just looking it up is we've found some common themes or common things, some rules. We notice, we observe, okay, every single compound we've tried that has nitrate ion in it, they all dissolve in water. And then we might find that things with carbonate in them, almost all of them do not dissolve in water, but then there's a couple of exceptions. And so this is an empirical method where people have tried these things and just put the results together and we get something like this. Ugh. So who's going to ask? Do we have to memorize that? Yes. It's not that bad. Okay, all of this stuff over here, not all, most of the stuff over there doesn't really need to be on this chart. So I'm going to explain this chart to you. So up at the top, we've got compounds containing the following ions are generally soluble. So if we've got these ions, just one of them, it's going to be soluble, except. So there's some exceptions. But the way you do this table is you start at the top. So does your compound have lithium in it? It's soluble. Done. Don't look any further. And you work your way down. Down at the bottom, we have compounds that are generally insoluble and some exceptions. If we start at the top and work our way down, we can erase most of those exceptions. So here we've got no exceptions, chlorine, chloride, bromide, and iodide. Those are insoluble if you've got silver, mercury 1, or lead. Well, instead of having all those words, how about let's just put the actual exceptions there. So get rid of those words. So except if you've got silver, mercury 1, or lead. And I won't try to trick you with mercury 2 versus mercury 1, so you can just remember mercury. You see mercury with chloride, insoluble. I won't try to trick you. Down here, sulfite, generally soluble, except with strontium, barium, lead, silver, or calcium. So here's lead and silver again. So that's not as much stuff, right? We get down here, hydroxide compounds are generally insoluble, except when they're paired with one of these guys. Well, if you have sodium hydroxide and you do the table correctly, you start up here, you see sodium, it's soluble, no exceptions, you're done. You're never going to get down there. So we can just get rid of that. We don't need that at all. So if say we're looking at, is sodium hydroxide soluble? what we should do is we should start at the top of the table. And in the first line, we see the ion sodium. Sodium ions are generally soluble, no exceptions. So it doesn't matter what the other ion is. Sodium hydroxide, sodium carbonate, anything. It's soluble. We're done. We say the compound is soluble. So we're never going to get down here if we have sodium hydroxide or lithium hydroxide, because we're going to stop up here. So we really don't have to put that exception there. We don't have to clutter our brains with it. And here we've got hydroxide and sulfide, and they're giving these separately, but the exceptions are both the same: calcium, strontium, and barium. So for sulfide, it's soluble. For hydroxide, it's slightly soluble. We're not going to care about the difference between those, so we're just going to do calcium, strontium, or barium. Those are exceptions. There. That's a little better. Calcium, strontium, barium. Calcium, strontium, barium. Okay, so it seems to be the same metals that are exceptions most of the time, right? So that helps. Carbonate, phosphate, generally insoluble, except, that's these guys up here again. These are the alkali metals: lithium, sodium, potassium, and our weird friend, ammonium. So if we start at the top and we're talking about ammonium phosphate, we're going to see ammonium first and say no exceptions, it's soluble. We're never going to get down here. So we really don't need to say anything about that either. Now that's a little more doable, right? So you remember the order here. This is alkali metals and ammonium, nitrate and acetate. These are halides, sulfate. And then down here we've got hydroxide and sulfide, carbonate and phosphate. And the way you learn this is when you have to predict the solubility of something, you try to think of the table in your head and work your way down. What was it? I have a picture of it in my mind. I can see it. And then you check yourself. You don't just automatically go look it up. Any questions? Mm-hmm.
Should we not be looking at the one on the green sheet then? Because I noticed it's like slightly different.
Yeah.
They have those
Excellent
slightly
question.
soluble.
What about the green sheet? Yes. I would recommend only using this chart and not using the green sheet. Not that the green card is wrong, but there are some other ions on there that our book isn't going to care about, and so we don't need to clutter our minds with those. These are the most important ones, and so these are the only ones you're responsible for knowing. And the difference between slightly soluble and soluble, most of the time, just doesn't matter. If it's slightly soluble, well, that's soluble, right? So I think it's better to just look at this chart and ignore the green card because it gets confusing.
And in the book, are there more than what's on this table here on the slide?
I don't believe so. This is a table from the textbook, and those are the only things that would show up on an exam. Okay, so predict whether each compound is soluble or insoluble. So we're looking at the ions. This has nickel ion and sulfide ion. Do you remember seeing nickel on that chart anywhere? No, because it wasn't on there. So do you remember seeing the sulfide? Was it on the top or the bottom? It was down on the bottom, right? Is nickel one of the things that we saw as an exception? No, we didn't see it anywhere on the chart. So we're going to predict that this is insoluble. And then let's go back to the chart and look. So there's no lithium there's no nickel anywhere. We come down here to sulfide. Exceptions. Nope, lithium is, lithium. Nickel, it's Lini. So what's the difference? Huge difference. No exceptions, so this is insoluble. How about magnesium phosphate? Insoluble. So magnesium doesn't show up there anywhere. It's not an exception. It's not one of the always soluble things. Phosphate is in the bottom. It's insoluble. So again, let's look at the table. So down there at the bottom, we've got phosphate. And the only time phosphate is soluble is with lithium, sodium, potassium, or ammonium, which we don't have. So insoluble. How about lithium carbonate? Soluble. Because in the first row, lithium, sodium, potassium, ammonium, soluble, no exceptions. Does it matter that the other ion is carbonate? Nope, it doesn't. This one's soluble. How about ammonium chloride? Soluble. First line again. Lithium, sodium, potassium, and ammonium, always soluble. Any questions? It's going to take some practice, but it's not that bad.